Hello, everyone. So today I'm going to talk about matrix effect on large geometry sims. Before that, I just want to present the sims team at UWA, composed of Luis, Paul Guagliardo, who is working on the nanosims, and Matt Veyalishin and Qing Zheng, who recently joined us. And also to thank them for all the work and support around the years. So my talk is about matrix effect. I will start by providing a bit of definition of the matrix effect. Then I will use some examples from the literature to illustrate the magnitude and trend. And then I will provide some practical advices about how to tackle matrix effect using large geometry sims. So why matrix effect matters? When we, as a geologist, we are interested to look at the geochemical record of minerals. And so in geoscience and also planetary science, in general, we deal with a great variety of minerals. This includes silicates, for example, which are composed of silicon-oxygen tetrahedron associated with different cations. So, for example, quartz, olivine, pyroxene, zircon. We can work with sulfide minerals such as pyrite. You have an example here, pyrrhotite, and carbonates, but also just within one single mineral group. Such as garnet, there are possible geochemical variation and complexities. So it is actually a bit of a problem because when we analyze these different minerals with our ion beam and our sims, there is actually a different fractionation of isotopes between these minerals. So, for example, if we consider a pyrite and a pyrrhotite with the same isotope computation in reality, in pyrite, 32S, which are a little bit darker here, are favored over the 34S. And therefore, if a pyrite reference material is used to correct the delta 34S sims measurement in pyrrhotite, then our delta 34S values could be off, biased by 4 per mil. So it means the results are not accurate, and that obviously can affect the interpretation of the results. So the matrix effect is the variation in secondary ion yield as a function of the sample's composition and structure. With the secondary ion yield being the number of ionized particles ejected by incoming primary ion. And so the matrix effect reflects the difference between minerals in efficiency with which atoms are sputtered from the surface and how the ejected particles are then ionized. The cause of this matrix effect on isotope measurements by sims is not well known. The difference in mass of isotopes can affect their energy and bond strengths within their matrix, which can explain why isotopes are sputtered and ionized differently. Although small, the difference in kinetic energy between isotopes means that they are not necessarily filtered the same way during transmission in the mass spectrometer, so that can also induce some isotopic fractionation. And last, the crystal orientation, which refers to the orientation of the crystal lattice relative to the primary ion beam and instrumental geometry, can also create some matrix effect. Although I will not talk about crystal orientation in this talk today. Just a little bit of maybe more mathematical definition that is really just to help us also to understand how the bias is represented also in the next slides. So we define the fractionation factor alpha between the isotope ratio of a material as measured by sims, A prime, and its reference value A. So alpha is a ratio between so R A prime and R A. And because alpha is usually very close to 1, it is practical to express this in per mil deviation from 1. So that's the definition of the bias here. And so using delta notation and some mass approximation, the bias is just the difference between the delta of the measured value and its reference value. So the matrix effect is estimated really as the isotopic bias between the value obtained by SIMS and normalized to a given reference material and its absolute value. So what are the parameters that affect the matrix effect on isotope measurement by SIMS? To illustrate this, I'm taking here the example of sulfur isotopes measured in different sulfide minerals, so chalcopyrite, pentlandite, and pyrrhotite, and they are all corrected using reference material that is made of pyrite. And here what we see, we have changed the size of the spot or of the raster we use. So here there's no raster, a 10 micron raster and up to 20 micron. And what we see is that for a given phase, the bias we observe between pyrite and chalcopyrite, for example here, it's nearly 0 with a large raster, but then it increases a lot. While we reduce the raster size. And that's a bit the similar trend that we observe in all these sulfides. So we only change the raster size, but we see that the matrix effect between the different phases can really change drastically. So that shows that actually the beam density affects the sputtering process in different minerals. And so any change in analytical conditions can potentially affect the matrix effect. So that's quite important. It's not because we have almost no matrix effect in certain conditions that it's the same for every conditions. So there is no model to predict matrix effect at the moment. The consequence is that the measured isotope ratios by SIMS must be calibrated using a matrix matched reference material. And when we say matrix matched, is same mineralogy, same crystal structure, and ideally same chemistry, which for real minerals is really difficult. The isotope fractionation is dependent on the relative mass difference between isotopes, and light elements are therefore stronger matrix effect. This limitation has made quantitative measurement by SIMS really challenging. And historically, the SIMS technique has long been considered inaccurate due to this constraint. And I just want to give a quote from Peter Williams in 1985 in one of his review paper, which I find summarize well all this first part. The difficulty of quantification that results from this sputtering and ionization complexities has retarded the acceptance of SIMS as an analytical technique. That said, we have found ways to overcome these challenges over the years. I just would like to now go through my second part, so to illustrate the matrix effect and some magnitude and trends. So basically, to overcome this matrix effect, we use reference materials with known isotopic composition and chemistry to empirically model matrix effects between minerals. So here, for example, I just show a very simple example of matrix effect in different sulfides, and we see that we can see a general trend here between with increasing of iron in the mineral. When we deal with complex solid solutions, so this minerals group with a lot of chemical complexity, then we really need to develop several reference materials with intermediate composition between the N members of the solid solution to model the bias as a function of this N member proportion. So here is just an example of garnet. It's a complex solid solution between an iron 3 plus N member, iron 2 plus magnesium, calcium, and manganese. And if we just look at the variation between iron 2 plus magnesium and grossular, we can see here the bias in per mil reported as a function of the X grossular is the concentration in calcium of garnet for a range of different composition of the reference material. So that's a bit the way we operate for this kind of complex minerals. We can see very well that the matrix effect, so this model of the bias versus the composition, is not necessarily linear. So it's not just we need 2 points to draw a line or 3. We need to test on more compositions than that. And it can be really significant. So here, for example, for the effect of andradite, which is the iron 3 plus N member of the garnet, we have nearly 10 per mil bias. And for example, the relative variation of oxygen isotopes in natural, in reservoirs on Earth actually is about 20 per mil. So it can really change the interpretation of the data. It's not negligible. Here, to illustrate the reproducibility of the matrix effect, I'm using the example of the magnetite siderite solid solution and the analysis of oxygen isotopes. Again, we can see the different composition of the reference material plotted in this triangle here. And here we're looking at the bias of oxygen isotopes, so in per mil, versus the iron content of the mineral. So we are looking at this portion of the triangle. And what we see in this example is that although the analytical protocol was the same, the matrix effect is not reproducible. So that's actually quite unusual from my perspective, but that's a reality. So it's really complex. And we can see that for low iron content of this mineral, the bias can be really, really strong. So more than 10 per mil. So yes, it's not negligible. Last, I just want to show you the example of the effect of magnesium content in olivine for magnesium isotope this time. And what we see in this example is that it's a function that is really difficult to model using conventional regression method. So very complex. And again, quite significant given the relatively small natural variability of magnesium isotopes in the different Earth reservoirs. So again, quite challenging. So two options here. Either maybe we have to wonder whether the precision is suitable for the scientific question that is asked. But if we have no choice, for example, when we analyze very small minerals in very rare samples, such as meteorite, we need to find new ways to tackle this problem. And that here, this new, very recent paper using more complex mathematical functions to actually try to model more accurately this kind of functions. And maybe the artificial intelligence could also help in the future to tackle this matrix effect. In earth science, we are interested in looking at whether minerals, especially sulfides, are recording mass-independent fractionation signatures because they tell us about the environment in the early Earth. This is a very rare signature, but it's not really the type of fractionation we observe in our instrument. So isotope fractionation in SIMS instrument is dependent on the difference in mass between the isotopes. So actually, mass-independent fractionation signature are not really affected by matrix effect. And here I'm just showing an example of a data set which contain different colors, which are actually different reference material of different type of sulfides. I reproduce the delta 33 versus delta 34. This is the mass-dependent line, and we see that the arsenopyrite and the pyrite reference material are on this line, and indeed, their true value does not record a mass-independent fractionation. In contrast, the ISUA, which is a pyrite, and Alexo, which is a pyrrhotite, all record a mass-independent fractionation, and the value we find is consistent with the real value that this mineral should have. So it seems that we don't need to have matrix match standard to obtain mass-independent fractionation signatures by SIMS. Here, I just want to mention the fact that from the examples in the literature, there doesn't seem to be there seem to be a quite reproducibility in the trend observed for some matrix effect between different between large geometry SIMS from different manufacturers. So here, typically, so Shrimp and Kameka. And I show here an example for olivine from Cicitano 2018, and here for garnet. And we see that so the two different data sets are very consistent for both type of instrument. In contrast, when we look at the paper of Euler 1997, where they really carried out an extensive study of the matrix effect by SIMS, but using a small geometry SIMS in different minerals, they see a quite different trend from large geometry SIMS. For example, here, this is the matrix effect versus as a function of the magnesium content of phospherite, and we see that it's quite important in magnitude at high magnesium content, whereas it's actually not really the case for large geometry SIMS. So we have to be cautious when we look through the literature for this type of information. I just want to also talk a little bit about biogenic minerals. Because it's they are very different from usually the minerals that we observe in rocks. So here is an example of I would just want to discuss about the example of aragonite. So biogenic carbonates are mainly composed of this aragonite. So it's a calcium carbonate, and it's a polymorph from calcite. So their crystal structure is different. And for a long time, it was hard to actually develop a reference material for aragonite just because it's hard to find homogeneous mineral. And so many studies have, in that case, considered relative variation. And that's also a way we can just deal with this matrix effect. However, some aragonite reference materials have been developed later, and there is a matrix effect that is between 0 and 3 per mil between these two phases. Again, so no chemical difference, but structural crystallographic difference. This is an example of analysis of oxygen isotopes in otoliths. So otoliths are little bones that are incorporated into the ear of fish, and they grow concentrically like a bit of a tree, and they record geochemical information of the fish environment potentially. And the problem of this material is that it's often quite porous. And they can have some elements that contaminate the analysis, such as collagen, so carbon or hydrogen or other elements. And this can actually be also a problem for the analysis. And I find it interesting in this study, they use a proxy to actually identify the presence of organic matter, so such as here the OHO ratio, and they can look at the bias potentially resulting from the presence of high content of organic matter. This is just another example as a biogenic mineral. This also can be bioapatite, which is usually very rich in OH. And the bioapatite you can see here is an example in vertebra, fish vertebrae. And we can see here the little crystals, and in between a strong porosity that is actually filled with some organic matter. So in that case, to actually try to identify any bias related to the presence of this organic matter, we used the carbon-oxygen ratio. And indeed, we can see that just plotting the delta 18O versus count rate of 16O or carbon-oxygen ratio, we can see that there is a strong bias related to the presence of organic matter. And we see really the variability compared to our nice apatite standard that is actually just a crystalline apatite from a rock. So very different. So now just a few practical advice with regard to the characterization of the materials before large geometry seams, thinking ahead of potential matrix effect on the analysis. I think really the very first step that is absolutely necessary is to start by the scanning electron microscope, to do backscattered electron image and EDS analysis to identify, first to confirm the mineral composition of the mineral you are actually interested in. For example, for sulfide, it's not always easy to just by eye identify which sulfide is what. It's also very important to identify inclusions. So you see here, it's maybe the grain is half millimeter in size, and you have all these small inclusions that we really need to avoid. We can observe if the material is porous, and we can also observe internal chemical zonation. And this is necessary also because we are using an in situ technique, so we really want to get the most of this technique. And if we don't have this detailed characterization work to guide us to where we should put the spot, yes, it's not. It's really to optimize the use of a large geometry scenes, and it's also to observe whether there's, for example, minor elements that are in high concentrations in the mineral we are interested in. So we want to know if there is any minor element. So that is with a very high concentration. We need to know if the mineral we are dealing with have reference materials. For example, in our laboratory, we have garnet standard, but not for chromium-rich garnet. So if the garnet is extremely rich in chromium, and we analyze it, we are not able to correct for the result, so it's a waste of time. And we also can get the structural formula of the mineral we are interested in. And in case of the polymorph, potential minerals with same chemistry but not same crystallography, the Raman is another technique that is useful for that. So, of course, the next step is really to discuss with the SIMS lab, where we want to do the analysis to check the reference material availability. And then for the analysis, where we have a matrix effect, there's two options. Either we can mount the reference materials within the mount, which is ideal, or we can also have one reference material with just one mount with the unknowns and one reference material, and then a master mount with all the other reference material. But in that case, the analytical conditions need to be really the same between the analysis of the two mounts. For garnet, for mineral with complex chemistry, such as garnet, which really needs a correction for internal variation in chemistry, it's really useful and necessary to go back to the, for example, electron microprobe to get really quantitative and precise analysis of the mineral next to the seam spot, and then the final corrections can be performed. This is just an example where we actually had this really interesting pyrite minerals. They show very strong variation in chemistry between the core and the rings. And specifically, they had very high arsenic content. We can see here up to 4 or 5%. So what we did here, and we didn't know whether that could affect the results. So we did the sulfur isotope analysis across the different domains, and we plotted the delta 34 against the arsenic content, and we don't see any trend. Usually when there is a matrix effect, there's really clear-cut trends. So we were confident that the results were not affected by this high arsenic content. This is just to show an example of a data set we obtained from measurement, for example, here in garnet, so again, mineral with complex chemistry. We have our main standard here that actually monitors the stability of the instrument during one session. And then we analyze some different minerals, some reference material with different chemistry. So you can see here we have two sets of measurements, and this data here are our unknown. So using this data in all our reference material, we can draw this curve here, where we can have we report the bias in permeable versus the grossular content of the reference material. And so using this curve, we can just correct the unknowns based on their composition in grossular. I find this really interesting approach to increase the accuracy of the matrix effect correction, is to actually include some of the, I would call them the deleterious elements, the ones that are creating problems in the mineral, into the analytical recipe. So here, for example, they added the analysis of iron, alternating with the oxygen isotope, so they have the exact iron concentration, the exact iron count rate for the correction. So yes, they are really. This is really interesting. I also just wanted to discuss briefly how we can identify a matrix effect in a dataset. That's always interesting from a quality control point of view. we can actually look at the count rate on the main isotopes, or secondary ion yield, so count rate per incoming primary ion. Because these count rates really reflect the concentration of the element we are analyzing in the mineral, and it's also reflecting the behavior of the mineral under the beam. So this is really dependent on the mineral itself, so really matrix dependent. So here, for example, we have that's a data set where so this is OGC. It's a quite famous zircon reference material for uranium lead and oxygen isotope analysis. And OGC is often contaminated by a few apatite grains. And you can really tell from the data that this is not all zircon, because we see here the secondary yields are very different between apatite and zircon. And the oxygen isotope is also very different. And that works also for unknowns. We can look at the difference in secondary ion yield between the unknowns and the reference material. Well, that works really for elements with fixed stoichiometry. For example, oxygen in silicate and sulfur in sulfides. But not for elements that are trace or minor elements with variable concentration. That said, as I said before, there's usually quite clear-cut trend between isotope ratio and composition when a matrix effect is present. Okay, and this is just a wrap-up of my talk. So isotopic bias resulting from the difference in composition and structure between a sample. Sorry, there is an isotopic bias resulting from the difference in composition or structure between an unknown, between minerals of different chemistry and composition, and this matrix effect cannot be predicted. So it is absolutely necessary to have matrix match reference material to ensure that SIMS results are accurate. This matrix effect is significant. It can be associated with complex functions that are not always easy to model. And this matrix effect can be affected by analytical conditions, but can be monitored by looking at ion yield and also proxies element. Okay, that's all for me.